Hi, welcome back. Last video we talked about the equation of a plane, and now we're going to apply the techniques that we've just been talking about with lines and planes to solve some questions involving lines and planes. Alright, first question. What is the angle between these given planes? Alright, so we could draw a picture of what these look like. Let me get Mathematica set up. 1 second. Alright, so let's visualize these planes. So if we want to use Mathematica to visualize a plane or to plot a plane, then the best way to do that, as long as your coefficient of z is non-zero, you take your equation of the plane, you solve for z, and you plot. So here, if it's x plus y plus z equals 1, you move the x and the y to the other side of the equation, and you plot the function z equals 1 minus x minus y using the plot 3D function. So we had one equation which was x plus y plus z equals 1, and we had another equation which was x minus 2y plus 3z equals 1, which, when you solve, gives us this. So here are two different planes, and what we'd like to do is we'd like to see what the angle is between these two planes. You can see there's two different options, right? There's either the option the angle is the acute angle, or the angle is the obtuse angle, but they're just off by 180 degrees. So whatever answer we get will tell us everything we need to know. Alright, so we want to know what's the angle between those two planes. So this, now we go back and we think, okay, we're using vectors. When we need to find an angle between two vectors, we use the dot product. Okay, we need to use the dot product, but in order to use the dot product, we need two vectors. And so we think, all right, we have a plane. What's the vector associated to a plane? So we had our two planes. And so we have these normal vectors to the planes, which we can read off of the coefficients. And then we can use the dot product to find the angle between them. Right, we have the vector here, and we can use the dot product to find the angle between those normal vectors. All right, so let's do that. So the normal vectors are 1, 1, 1, and 1, negative 2, 3. Remember, we're reading off the coefficients of x, y, and z in these equations, in the standard form of an equation. And then we know that the cosine of theta between two vectors is equal to a dot b divided by length a, length b. So in this case, a dot b is equal to 1 times 1 plus 1 times negative 2 plus 1 times 3 divided by square root of 1 plus 1 plus 1 times square root of 1 plus 4 plus 9. So that gives us 1 minus 2 is negative 1 plus 3, so that's 2, divided by square root of 3, and 1 plus 4 plus 9 is 14. 3 times 14 is 42. So cosine of theta is equal to 2 over square root of 42. And so theta is equal to the inverse cosine of 2 over square root of 42, which I have on the next slide is about 72 degrees. All right, so let's go back to the Mathematica and check to see. It didn't seem, we thought maybe the acute angle would be rather acute. Let's see what what's happening there. The main reason why this looks like it's less than 72 degrees in terms of this angle is because of the scales of the axes here. So the thing we need to do is we need to tell Mathematica to not rescale these axes. And to do that, we talk about box ratios. All right, and here, now we go. So what box ratios does is it says, I want the ratio for the x-coordinate and the ratio for the y-coordinate and the ratio for the z-coordinate to all be the same. And let's see, is this actually right? So this distance is 1, but this distance is 2. I think that's not the right way to do it. I think what we want to say is automatic. Aha, automatic, that's the right one. So now if you see the distance between 0 and 2 here looks like the same as the distance between 0 and 2 here. So now if we look at the angle between these two vectors, that does actually look, between the two planes, it does look like 72 degrees. So you do need to be a bit careful here in Mathematica to be explicit about what type of box ratios you want so that you're getting the full view of what the picture is. All right, let's go back and do another example. All right, we can also ask the question, what's the equation of the line, the intersection line between the two planes? Okay, so here we have our two planes, right? Then they intersect in this line. And so the question is, what's the equation of that line? So to get the equation of a line, you need a point and you need a direction. And so how can we get a point? And how can we get a direction? So in order to get the direction, well, the direction corresponds to a line that lies in both of these planes. So somehow we need to get this direction from the normal vectors. So what's special about the normal vector to this plane and the normal vector to this plane compared to the direction of the line? Think about it for a second. Well, we want the direction of the line. It's perpendicular to the normal vector to this plane and perpendicular to the vector from this plane. So, to get the direction of the line, we want a vector that is perpendicular to both normal vectors. How do you get a vector that's perpendicular to two other vectors? Cross product, right? So the direction of the line is going to be 1, 1, 1 cross 1, negative 2, 3. All right, and so that's the direction of the line, and we also need a point of the line. And the point on the line must satisfy both equations. So I'm going to just choose a nice point, a nice value that's going to make it easy to solve these equations. I'm going to choose z equals 0. And I'm just choosing z equals 0 because I want to get rid of this part of the equations, just so that I have simpler equations to work with. Notice I didn't have to choose z equals 0, and it's also possible that z equals 0 doesn't work if you never go through the xy plane. But if you do go through the xy plane when z equals 0, we can plug in z equals 0 into this equation and solve for x and y. What do we get? X plus y is equal to 1, and x minus 2y is equal to 1. I'm going to multiply this first equation by 2 and then add it to the next equation. So what do I get? I get 2x plus 2y is equal to 2. X minus 2y is equal to 1. If I add those two together, I get 3x is equal to 3. X is equal to 1, and so y is equal to 0. So this plane goes through the point 1, 0, 0. This is the x-coordinate, this is the y-coordinate, and this is the z-coordinate. All right, so we know the direction, and we know the point, 1, 0, 0. And so we could do this by hand. I'm going to go over to Mathematica and calculate that. So what did we want? We want the cross product between 1, 1, 1, and 1, negative 2, comma 3. There's the cross product. And what we said is the point 1, 0, 0 lies on both of these. So let's now show this line in here. So we're going to show, first I want to create a graphics object. I'm going to put it after my equation so that I use that same, when you use the show command in Mathematica, it always puts everything in the first picture. So I'm going to show this first picture, and then I'm going to show a parametric plot that starts at the point 5 minus 2, that's the direction, at 1, 0, 0, in the direction 5 plus t times 5, negative 2, comma negative 3. T goes from negative 1 to 1. And let's make it bright red. Plot style goes to thick red line. And we can see that that line does indeed go right through both of the planes. And let's put that point that we liked in there. This is a graphics object, graphics 3D at 1, 0, 0. What do we want? We want a point there. And let's make that a large point size. Large. And we're going to make it a black point. Where are you? There you are, right there. If we zoom in, we can see our point. Maybe we need to not, let's make this point size not just large, but we'll make it point size 1. That's a bit big. Point size 0.1. And we can see this point. It's right there. I think I'm going to make it a sphere instead of a point. I'm going to make it a sphere with radius 0.05. That's still too small. 0.15. There's our point. There's our point 1, 0, 0. And there's the line that goes through the point, and that's the intersection of the two planes. All right, I'm going to stop here. I'm going to do one more example in another video. See you soon.